Hello Abaqus user. Welcome to Abaqus Acumen for quick and sound learning. Today's session we are going to do on the modal analysis or modal dynamics. This type of analysis are linear perturbation analysis, and they are not very hard to perform it. It's just straightforward process in Abaqus, which you can do it for the modal dynamics. But before we start this problem, we'll first look why it is very important for us to understand the natural frequency of any system, body, or a part. And to start with that, we'll quickly see a video, a real life resonant condition, because when the loading frequency and natural frequency match, resonance happen and structure can fail. So first looked into this Tacoma narrow bridge collapse. This was collapsed in 1940, and it was a classic example of a resonance condition. Now very specific to this bridge, the wind was blowing, and at one particular time the wind frequency matches with the bridge frequency, and then you see a excessive deformation of bridge and then collapse. So now you see this is a real life resonant condition, and to avoid any structure from getting resonant, we should know first what is the structure natural frequency. Now once you know the natural frequency and then loading frequency, you can avoid this type of situation, resonance. So you can see the lone car there, and then it started, its very high deformation started. The bridge is in resonant condition with a wind load, and then on YouTube you see this full video. It's again very classic video on the resonant condition, and then very high deformation, and then I'll just move it forward. So this looks horrible. You have very excessive deformations, and then we'll look something and totally collapse. Now it collapsed. Now this is exactly a real life problem, but we'll try to solve this. First we'll get much more understanding on the modal dynamics. So friends, this is our specifically a first video into dynamics part. Most of our videos on the static part or quasi-static part. So we started with modal dynamics. This will be our first lesson. In the first lesson is we are going to do is a modal dynamics or getting a natural frequency of system. Now this getting a natural frequency of system within Abaqus is a straightforward things, but the important question need to answer is why specifically we are interested in the natural frequency. And to really explain why it is very necessary to understand the natural frequency, I just plotted a amplitude ratio versus the frequency ratio graph. Now this is available any theory of vibration book, or it is if you do googling, it is available on the net. But this, once you understand the phenomena of frequency ratio and the amplitude, then it is very easy to connect that to natural frequency, and then you'll understand why it is important to get a natural frequency of the system. Now this is where the loading frequency and natural frequency match. This is exactly equal to 1. This is exactly a resonant condition. So if you have undamped system, then it will have infinite displacement, and then once you added damping, then this displacement reduce quite a bit lot. If you have some external damping, viscous damping there, then you can control this, but structural damping is just a 5%. So if natural frequency match with a loading frequency, it will have a very high deformation. So that is what exactly it shows, and this amplification ratio will be then connected to your static ratio. And then I'll not go in much detail about this phase lag. We'll have a separate session on this, but That's where, to understand what is a structural natural frequency and then compare with the loading frequency, you need a natural frequency. Now once you looked into this, when the ratio of loading frequency by natural frequency trend towards 0, that means you assume you are sitting on a chair, say every 5 minutes, then your response is more like a static response. So this is like a your deformation. Static deformation is nothing but a stiffness of the spring divided by the loading frequency. And then specifically when you see crossing this point, you see the response where actually the loading frequency is higher than the natural frequency, then response is not even a static response, it is much lower than a static response. So that means if somebody start putting load very frequently and the ratio of the loading frequency is very high compared to the natural frequency, then you don't have to you don't have to even bother about the dynamic condition. Then you can just do a linear static analysis or static analysis, and then you know for this type of ratio where actually loading frequency is higher than 2, then you don't bother about it in dynamic response, because you know your dynamic response is even lower than the static response. The only area which is actually we are concerned is the area which is near to the natural frequency. So this is the band actually we should look, and we should avoid the structure getting here. I'll not go into the phase loading within phase and phase lag. We'll have a separate session on this steady state dynamics or transient dynamics. So now we'll move to a very simple question now. First, if we can understand this, then you can connect each and every part of a dynamics, like a modal dynamics, transient dynamics, everything. So take an example of swimming board where person can jump. Now we'll try to correlate with this diagram. So if the natural frequency of this swimming board match with the loading frequency, so the person come, then next person come, and then match, then you'll have resonance. So something like you'll be in this region. Now a person come, hit this, jumping off, the next person come after 10 minutes. So 1 divided by 10 into 60, that is your loading frequency. And then if you take that ratio, and then you understand, then the natural frequency is quite lower compared to the loading frequency. You are getting into this region. So this is nothing but a static analysis. So person come, sit on this. So your response to this type of time dependent loading is nothing but your static loading. So it is almost closer to a static loading. And somebody comes and jump very frequently. So one come jump, very fast jumping, or just this guy dancing on this, start putting some movement, then your loading frequency is higher than natural frequency. You are into this region. So your response is much lower than the static response. Now we'll start with the natural frequency. First we'll understand. First we'll get basic clear, and then we'll go to the problem. Now this is, I've taken a single degree of freedom system. You have spring and mass, and there is no damped. So this is undamped natural frequency. So if I just disturb this, I just pull it back, and then leave it. So from equilibrium position, I just pull it some distance, and then I leave it. It will just move to two extreme position from the mean position up and down, and it will just keep on going this. So this is we are taking a undamped condition, and it will just keep moving. And then your frequencies, if you take a 2 peak, or you take this time interval, and then this time interval, if you do it one by time, that is nothing but the natural frequency of system. So if you take any system, you disturb it, it will start vibrating in its natural mode. So this is only 1 degree of freedom. So So you are seeing only one mode shape, up and down. So this is just a axial mode you are taking because it's a 1 degree of freedom. Now let's quickly not go into much detail about fundamentals, but first understand what is spring mass system. So you have a spring, you have a damper, and that is connected to a mass. So you have mass, you have damper, you have damping coefficient. So we'll just write a Newton's law of motion. So mx double dot plus cx dot plus kx is equal to force. This is the, so if you have something like external force, so I'll say external force, you move it by x, so mx double dot, this is called as the inertia force. This is called your damping force, and this is nothing but a spring force. Now in case of natural frequency, you don't have any external force, so external force is nothing but 0. So if I plot this equation, if I write this equation mx double dot plus cx dot plus kx, it's nothing but a 0. Now very specifically the damping. Now there is a damping, but why we don't have to take this damping in the modal analysis? Because any structural damping you take, any structural damping in the world, the damping is less than 5%. So the damping force, unless you have some external damper there, you take any system, the damping is 5%. Damping ratio is 5%. So if you take that 5% damping, this is nothing but a negligible. This amount is negligible, so you can neglect it. And then you put mx double dot plus kx is equal to 0. Now this is nothing but your straightforward linear equation. And then if I try to find the root of this, so it is x double dot k by m, x is equal to 0. And then if you solve this linear equation, your natural frequency come under root k by m. So same thing, x is equal to plus minus under root b square by 2a. So that solution you can use, and then you can get under root k by m. So your natural frequency of any system is dependent on the two part, the spring stiffness and the mass. This is nothing but it is in radians per second. So this is rotating natural frequency, radians per second, and then if you want to convert it, you can do a 2 pi omega n, then you get a frequency in hertz. And that frequency, if you do 1 by frequency, that hertz, you get a time interval, how much time interval. So this time is nothing but, if you try to connect here, this is your time. So if you do this 1 by time, you get a frequency in hertz, and then you can back calculate. So anything, the major takeaway from this is your natural frequency is function of stiffness and the mass. So this stiffness is your modal stiffness, geometrical stiffness, and then this mass corresponds to that. Now lot of time this question come is why we are not doing a damp natural frequency, and the answer for that, this is your answer. So your damping ratio is 5%. So if you try to solve this problem, undamped to damped natural frequency, the ratio, so it's 1 minus 5%. It's nothing but 5 divided by 100, so 0.005, and then you take that root, it is nothing but 99.95. So putting a damping and solving the Laplace equation, you get the frequency between damp and undamped, they are not much, very much different. Now with this, we'll try to solve this problem. We'll take a specifically I section, structural I section, and then we'll try to build it as a cantilever. We'll give density, we'll give elasticity. So from density you can calculate what is a mass, and material stiffness, and you can get from material. Geometrical stiffness you can get based on the boundary condition and the structure what we have. So this is a problem. We'll try to do it. So we'll quickly do the problem. So so this is exactly what we'll do. So let's put new. In Abaqus there are two different methods are there, Langcos and subspace. You can get all this information doing googling. Subspace is when you have extract some minimum number of eigenmode, then you can use subspace. Langcos is more efficient, and then you can use it. We are going to use the Langcos. So we'll just quickly put this into a shell. So I'll put coordinate 0, 0, then 25, 50 minus 25, 50. So that way I get the 2 point, and then I'll put a 0, 50, 0, minus 50. So that way I get a bottom point, and then I'll put 25, minus 50 minus 25 minus 50. So I get this point. So we can quickly start putting. We'll connect this. So we created a I section. Now this was 100, so I'll just, for your reference, I'll just add dimension. So this is 100. If you want to measure, you can measure this. We'll just add dimension. So you have 25, 25 both sides. So we'll just extrude it by 1000. So we will extrude this by 1000. So that way you get a I structure. Now we are going to put a cantilever condition. Now this is a simplified problem. So this is undamped, no pre-stress in the model. That model then will based on this video will build other important modal dynamics part. So for this metal model, it will be steel. We are going to use ton, Newton, millimeter second. So density I am going to put in ton per millimeter cube. So it's a 7.85 e power minus 09. This is in tons per millimeter cube. I'll add elasticity part 210 e power 03 MPa, and then 0.3 is a Poisson's ratio. We'll put thickness as a 5 millimeter, and then we'll assign this to this structure. So we assign it. Now we created a part, we created a property. Now we'll quickly create assembly. There is only one part, so that will be in assembly section. Then we'll quickly define the step. You can give any name what you required. We are giving frequency. So it's not in general, so this is important. So you try to do a modal analysis, you want to find the frequency of structure, you go to the frequency. It is not in general, it is a linear protrusion step. Then you say frequency, and then we say Langcos, and you have different option. We'll have a separate session on this frequency shift, minimum frequency of interest, and everything if required. So we'll select then we'll extract what is a specific we'll request them number of eigenvector all in the frequency range. We'll say we want 6. So we are looking into first six modes, and we created step. We don't have any contact anything, so we don't have interaction. Load will be only one thing. We are going to fix one end. So this particular end I'm going to fix it up one end. So this represents the cantilever section. So it will be have end caster condition. So to select all the edges you can have set. I'm just putting a shift option and clicking it. So that's where we'll put end caster condition here. So we put end caster. We'll quickly do a meshing. Meshing you cannot do in assembly. You have to do in meshing in part. We'll select it chord medial axis, which give very good structural smooth mesh. And then for modal analysis, most of the people say you don't have to do very fine mesh, which is absolutely right. But if you have very coarse mesh, it doesn't really capture the mode shape. So it will give you what is the frequency, natural frequency number, but you have to really capture the right mode shape. You should have a reasonable mesh. Again, we are not saying it to be very fine, but it should be a reasonable mesh which should capture the modal mode shape. So I'm going to put 7.5. So then we'll select it's S4. So by default it is S4, and then we'll mesh it. You done this, we'll just save this problem. Modal frequency, and then we'll create job name. We'll have a data check. It's most of the time it is better to do a data check, so that way you find out if there is any issue related to pre-processing. So I think just to recap, we are trying to capture the natural frequency, and these are very important in terms of modal dynamics or dynamic analysis. So dynamic analysis is connected to time. So whenever force is connected to time, it is a dynamic issue. And then to solve the dynamic any problem, first you should know what is the natural frequency of the system. So we are almost done. So we'll see what is so this is our the first mode. So let's first check what is the different mode. So we have put a first mode. Now once you select the first mode, so the first mode is 29 cycles per minute, so cycles per time, and then you select this animate harmonically. So the first mode is your lateral bending. Now why we have first mode as a lateral bending? Because if you remember, the omega is under root by k by m. So if you have low stiffness, then that's what actually you'll get for frequency. So lateral direction you don't have much. The I section, the major stiffness is the bending, and that against I section. So this is the lateral bending, because it's not perpendicular to the I section. So this is what your first mode. So first is a lateral bending. Second mode is your torsion. Now this is not a closed section. So if you want to have a high torsional rigidity, then you should have, I'll just reduce the scale factor. I'll just make it 25, because 100 it was showing a lot of it. Again, this displacement number have zero meaning. It doesn't mean that during the natural frequency this should be displacement. It have zero meaning. So second mode, what we see is a torsional mode, because this is not a closed structured. I section are designed for the bending, so it's not a closed structure, so you see a torsional mode second. Third mode is our bending mode. So this is the bending mode. So our third mode is a bending mode. We'll see what is the next one. This is a second lateral bending. So the first one was the first lateral, this is second lateral. So it was like a cantilever shape. Here now you see a double curve. So this is a second lateral. Then we'll see what is the fifth one. Fifth one is a second torsion. So fifth one is a second torsion. Then we'll see what is the sixth one. Sixth one is a third. It's combination of twisting and lateral. So this is what actually how to read mode shape, modal things. Now quickly we'll go back and we'll see what we have done. So we first seen what is a resonance and why resonance is connected to the natural frequency. So any problem, dynamic problem you want to solve, first get a natural frequency. Second thing, we understand damped versus undamped frequency. So any structural damping in the world is less than 5%. So you don't have to worry damp and undamped natural frequency. Third thing, we are done solve this problem in Abaqus. So you have Langkos and subspace method, and we briefly understand the amplitude and the frequency diagram. We'll really have a separate session on this, how to do this. But this is what actually we are learn. If you have any query, send it to abacusacumen@gmail.com. Don't forget to like us and subscribe us. This is our first video in the dynamics part, so we'll bring other video like a steady state dynamics, transient dynamics. Those things will bring for you. Thank you. Bye bye.